Good afternoon, everyone, and welcome to the UIM Water Utility Infrastructure Management webinar series. This is Andrew Farr, Associate Editor with UIM, and I'm very happy to introduce our webinar today on permanent leak detection systems, exposing and addressing invisible operational risk. The webinar today is presented by Ecologics and will explore current available technologies in leak detection, thereby exposing otherwise hidden operational risk and offer solutions applicable to small, medium, and large water utilities. So just a couple of reminders for attendees before we get started. During the presentation, you can view the PowerPoint slides in full screen by clicking the box in the upper right-hand corner to expand the screen. During the presentation, you can also send questions to the presenters through the questions panel, which we encourage attendees to do so. And you should see the question panel on the right-hand side of the screen with a questions box. And at the end of the presentation, we will hold a Q&A with our presenters. So at this time, I'd like to go ahead and introduce our speakers today, Stacy and Marc Bracken. Stacy is Product Manager for Ecologics, joining the company in 2013, and he is working closely on research and development and commercial operations to deliver innovative technologies that exceed customer needs. Eric has more than 12 years of experience in multiple areas of the high-tech water industry, including treatment technology, water-focused venture capital investing, and more recently, asset management technology with Ecologics. And then we're also going to have Marc Bracken, who is the Vice President and General Manager of Ecologics. Marc has more than 18 years of experience in acoustical and vibration engineering and 11 years of management experience in the water industry, and is an innovative solution provider in acoustic leak detection, pipeline condition assessment, and non-revenue water. So Eric, whenever you're ready, take it away.
Okay, thanks very much, Andrew. So I'm Eric Stacy, and with me here is Marc Bracken. And let's get right into it. That was a great introduction. So this is the third in a series that we've done with UIM. The first one was, I think it was earlier last year, we did a webinar that was Innovation and the Role of Criticality in Transmission Main Management. So in there we postulated the need for more frequent monitoring on the most critical transmission lines. And really the best way to do this is through a permanent monitoring solution. The next, on the right-hand side, we published a white paper, I think just back in December actually, arguing the case for permanent leak detection. So this confirmed the most critical pipe segment versus just acceptable critical, and also that permanent monitoring makes operational risks that were once considered acceptable or normal are now considered undue, or now should be considered undue. Now this third publication in this series here, we go deeper into permanent monitoring. And we're postulating here that permanent monitoring is it's disruptive to traditional pipeline management. And we're also bringing distribution into the picture here. So we'll be focused on distribution and transmission mains. So getting into transmission versus distribution, there's lots of differences. We've highlighted a couple things here are pretty standard. Most people will recognize them. What we've done is we focused on what's common between the two. So they have unique failure mechanisms. There's also a need to find leaks early and to prevent bursts. So what we've come to the conclusion is that with these distinct risk factors, and then knowing there's some commonality in between them, we've set about developing products that are unique for both distribution and transmission. So now we'll go into transmission main management. So what's showing here on the screen is a typical maintenance workflow, and I'm going to start by thanking our friends at Philadelphia Water for the graphic here on the right. This is not something we put together. They've got some great information for their citizens on there. So thank you. It's referenced there if you guys want to have a look at that. So typically you have leak detection crews or a citizen will spot water in the wrong place, and they pick up the phone, they call 311, or they call the water department. From there, crew is dispatched to go identify, maybe contain. You're going to pinpoint, repair, and restore. All this is very standard. This is common for utilities in the U.S., Canada, Europe. This is all a very reasonable approach. The thing to note is that it's generally tolerated by utilities and customers. It's the normal way that things are done. So we're going to pause here to ask the poll question. And now I'm going to turn it over to Marc Bracken here. We're going to talk about some technologies.
So we're going to start off just by reviewing what's currently available in the market. If you look at what people are currently doing to proactively manage their transmission mains, there's 3 technologies really. There may be a 4th or a 5th with infrared, but the primary ones that are being used are gas tracing surveys, insertion surveys such as Sahara, SmartBall, and correlation surveys such as Ecologics does. And we've outlined a description and some of the pros and cons of these, but the common thread of the problem with this is it's a snapshot in time. It looks for a leak that might currently be occurring on a transmission main, and it's not to say that as soon as our crews walk away from that main that a leak does not occur the same day or the next day. And that's really goes to the risk of these types of mains and the fact that very little is being done to actually proactively find leaks on them. And when it is, it's done as a point in time.
So it sounds like you're more addressing the symptoms then, right?
More addressing the symptoms than the actual risk of these mains. Correct. So if you look at what the next generation technologies are, then there's a number of them out there. I'd like to really look at how fiber optic in a sense has transformed the way people manage their pre-stressed pipes. When that technology came out, it afforded utilities a way of proactively looking for wire breaks that would be a precursor to catastrophic failure. Unfortunately, the downside of that technology, it's really only applicable to one type of pipe, which is pre-stressed concrete pipe, and it doesn't find leaks. The permanent correlation methods, on the other hand, can be applied to any pipe type, and there's a lot of evidence that many of these pipes will leak before they fail. And along with some of the other analytical information we can get out of them, it now provides the opportunity for utilities to not only look at their pre-stressed pipe in this way, but all the other types of pipe in their transmission main network.
So you're talking about changing standard practice.
Again, changing standard practice. We think this is something that when people see the risk mitigation that can be done, it will be something that can't not be done.
Perfect.
And use a double negative. So we're going to show you a technology case study of how we've implemented this technology in a 24/7 monitoring. About 8 years ago, Ecologics started having a lot of success at performing correlation on large diameter mains. Really, before we came into the market, it was felt that this was impossible, actually. And we've now found over 500 leaks on large diameter mains, the largest of which, for the record, is 108 inches or over 4 meters diameter. The logical extension of this technology, again, because it's a point in time that we're looking at it, is to find a way to put this technology onto a pipe permanently. That's what we've done. And what you can see here is the 4 components that make up this. There's an antenna that connects to GPS and cell networks, a power source, processor and communication hardware, and a sensor to determine the leak. So looking at this a little bit more closely, the technology to do this was literally not available 5 years ago. When we looked at what was required, these systems are remote. People very often can't run power to them. They can't run telecoms. So we needed to develop a system that was battery operated, very low power, but very, very powerful, because correlating leaks on transmission mains is far more complex from a signal processing point of view than doing it on a 6-inch or 150 millimeter distribution main. Really, the DSPs that we're using these low power DSPs and the power that they have even as late as this year, we've upgraded on the system. So this is new technology. I want to emphasize that. At the end of the day, though, we had two requirements, and that is that the system had to be simple to install, and it had to be very, very reliable. So in these diagrams, you can see the simplicity. It's two boxes on the side of a chamber wall and a sensor into an air valve or other appurtenance in the pipe. The antenna mounts on either a lid or on a pole. There's many ways to do this. And in terms of reliability right now, we're running a very, very high uptime on our systems in the order of above 95, 99%. In terms of the architecture, this is really just an M2M architecture. It's very, very simple. It runs on cell phone protocols, on standard communication protocols. It has a web-based client and control interface. Typically, nodes are located about every half mile or about 3/4 of a kilometer, 750 meters. The cellular network then connects to a server, and a lot of the heavy lifting on the signal processing is done on the server, and then displayed on a standard user interface. It's also very flexible architecture in that we can incorporate customer requirements as APIs, and we can attach, as you're going to see, other sensors. So if you look at how we thought of this problem, when we would talk to potential clients about this as sort of a voice of the customer, when we said we can do leak detection and early warning of leaks that could become catastrophic, people were certainly interested. When we told them that we could then do pressure and flow on demand, not just necessarily being sent once a day, when we said we could do temperature and chlorine and pressure transient monitoring, all of a sudden people started to have a different idea. This is truly monitoring. It's not just a leak detection system. So if you look at what we've done here, the permanent leak detection system is not just a permanent leak detection system. It has 24/7 operation, and the thing never sleeps. So what that allows us to do is on-demand and alerting to any kind of threshold. So in other words, if you change something in terms of a pumping variable in your pump station and you want to see what effect that would have instantaneously on your pressure and flow throughout your system, you can instantaneously wake this up. And most data loggers, you can't do that. If they're GPRS or even 3G, they're asleep most of the time because they're essentially a cell phone and they wake up at a predetermined time and send you the data. This system is not like this. This system is always on low power awake mode, and we can wake it up at any time we want and get an entire day's data at will.
Okay, thanks, Mark. So now with all that in mind, let's revisit operational risks now and look at it through that lens. So in these categories here under bursts, in the past you have emergency repair crews. You have crews on standby. And if you think about this, it's akin to having fire department and an ambulance, like an emergency service department, that can be dispatched at a moment's notice to go and isolate and repair valves. The imminent approach with this technology, what it offers is the ability to repair leaks before they burst. And this is planned. This isn't something that you've just caught a leak because you saw a bit of water and fixed it before it burst. The technology is designed with this in mind. Frozen isolation valves. This is a big risk that you don't find out about until you've had a catastrophic burst and you're trying to isolate that section. These valves may not have been operated for the last, could be a period of time. They could be broken, and you have to start isolating larger and larger surface areas. If you can plan this, you can have a crew go out and exercise those valves and do repairs as necessary on the valves before repairing the leak. Then we have leaks, which we already talked about. And the one that Mark just mentioned at the end there is pressure and flow. So you typically can measure these at pump stations. This allows the ability to push that out into the system at other points. It's not just pressure and flow. We're talking water quality as well, should that be necessary. So really, just to paint the picture here, we're offering tools for responsible mitigation of risk. Consequential damage, that includes boil water advisories, efficiently allocating labor, And also water loss reduction is in there as well, but that's a little bit further down the list when you look at the risks associated with these types of mains. So we'll now shift our focus from large diameter to small diameter. I'm going to pass it back over to you now, Mark.
Yeah, thanks, Eric. So a lot of the things that we just talked about on transmission mains are the same on distribution mains, with perhaps not the same level of criticality. But again, there's lots of times where small diameter mains create huge bursts and a lot of consequential damage. And there's a lot more bursts on small mains than there are large mains. So again, if you look at the way most people do it is they may do a leak detection survey. We love the idea of a crowdsourced leak detection.
More the description than the idea of it.
Yeah, more the description, that's right. But that is what's happening with a lot of leak detection. And as you're going to see, one of the pilots of our distribution leak detection system, one of the things that our clients really love, and Eric just talked about this in the last slide, and it's very applicable here, is they love the ability to manage the repair of leaks, to understand how bad they are they growing, how big they are, and really allow them to plan ahead and do this in a controlled manner, not as an emergency.
So there's an interesting question here at the bottom, and I'm sure everyone on the line has read it, but this is another one of these thought exercises we're kind of putting out there. But really, if you reduced your emergency repairs, you have excess budget all of a sudden. That's
right, and when we're looking at potential clients and we're talking to them, one of the things, we don't just want to know what their non-revenue water is, we want to know how much money they spend on catastrophic failures and emergency repairs.
So we're going to pause once more for another poll question here.
And this is one that we've bandied about in the office quite a bit, but would be very interesting to see what some of our utility listeners have to say about this. Okay, so moving on, as we looked at for transmission mains, we're just going to look at what the current technologies and approaches to leak detection on distribution or non-revenue water. And we've put 3 of them out here, and these are all good things. DMAs, district meter areas, is essentially the practice of sectorizing your system and measuring minimum nighttime flows. And understanding what your leakage rates in those areas are, and then prioritizing the high NRW real loss areas for intervention. This is something that's very common internationally, and by that I mean outside North America. It's very, very rare inside North America for a number of reasons that we won't get into. And then the most common one would be a sounding survey, where you go hydrant to hydrant or valve to valve or even service to service to listen for noise. And then finally, in the last few years, noise loggers have been deployed, again, as a survey technique. And one of the, or I guess some of the problems with these in general are high false positive rates, particularly on noise loggers, that just because a noise logger tells you that there's a leak there doesn't mean it's a leak. They're really a noise logger, not a leak logger. Leaks can be identified, but there may be a lot of labor involved in actually pinpointing that leak. And again, you're reliant on specialized labor. These things are usually done by highly specialized people. So again, as you read on our bottom box, the current technologies really focus on improving a manual process, and it's still an exercise in hunting.
So it sounds like it's a step in the right direction, and then you look at the next generation of technologies, and I think you've got competitors, you've got the marketplaces that has recognized this, and there are alternatives out here now. So you have your multi-parameter analysis. This is some really interesting stuff that's happening on a within a wider network, where you're looking at flow and pressure, and then doing some predictive analysis on that. It does leak identification, but really these are all secondary indicators. But they actually mesh well with things like a SCADA network and other control level things. And then the permanent correlation, and this is where we fall in. So we started off by saying it's a distinct solution. When you're talking about a distribution network, it's a grid. It's not linear like a transmission main typically is. So a mesh network is what you're really looking at in terms of the communications. When you're doing, it also allows for correlation now. So you're getting into multi-channel leak detection. So you've got the new information now, and you get it with both of these things. And again, it's thinking about what standard practice looks like all of a sudden. So you find your leaks before customers do. That's actually, I'm going to underscore that. So you're not necessarily in the crowdsourcing thing. Customers are probably going to start to get upset if they are the ones that are responsible for working with utilities to find leaks. Monitoring leaks in the repair queue is the other thing too. It's just not possible in many cases to get to all the leaks as they form, but you can queue them up and you can schedule your labor. But while you're doing that, you can monitor it as standard practice, and also notifying customers early as standard practice. So what we're getting to here is that the status quo is starting to look a little bit different now. You're looking at operational risk a little bit differently now. So technology case study. This is our technology that we offer. It's based on the same platform as what Mark had talked about, but it's a different arrangement. So we start with a sampling node. It's installed in a hydrant cap, above ground in a hydrant cap. These are and similar to the previous technology we discussed. Still, it's an antenna. It's a battery power source, and we've got our processor and our sensor. It's mounted in a hydrant cap, and that hydrant cap is then screwed onto the hydrant. There's some approaches here that differ. We've seen people using hydrophones versus surface mount sensors. We very purposely designed a surface mount sensor, and this is one of our core areas of IP. It's a very sensitive sensor. Listen, I'm shamelessly saying that there's nothing like it on the market. We haven't seen any other sensors that are this sensitive, and the proof of that is that we can mount these in hydrants, and we can mount them pretty good distances apart. When you're doing a hydrophone, you're getting into the water column, and with a hydrant, that can get quite difficult. It's getting below frost line in a lot of cases. But really, this above ground moves all of the equipment from a hostile environment in a valve chamber or an underground pit on a road that's getting silt and water and salt exposure to above ground. It also helps out the network stability considerably. So the mesh network is your hub and mesh format where you have a collector, and then you have nodes installed around the collector, and they're all speaking to the collector or to one another. One of the very important points here is that you have the ability to do a system-wide correlation. You have the ability to do a system-wide sweep for leaks at any time, and that's something we actually do on commissioning. This catches all the leaks that exist in the system. It can be a bit overwhelming for our customers because now you may have had your queue of leaks. We're going to find those, and we're going to point out other leaks you necessarily didn't know about. That being said, you can now still monitor them as well. So there's the risk mitigation here. And then you have your baseline noise for a background. So there's options for this. I've shown this as a mesh network, an RF network. This is for larger installations, in the hundreds of nodes. If you're looking at smaller deployments, in the dozens, there's a cellular-based solution that we're in the midst of developing right now as well, and that'll target smaller installations. Network architecture, nothing revolutionary here. It's nodes speaking to a collector, to the cellular network, directly to the cellular network, and this is how we monitor service area. And then there's the typical user interface as well. Leak detection is where we stand apart, or where it starts to get a little bit different from the current technologies that we had talked about. Primary leak detection, or single-channel leak detection, is happening at the node. Each individual node, or in this case a hydrant, is determining the likelihood that it hears a leak in its vicinity, and it passes that information over the network to the back-end server. It also passes information about its health, its battery life, communication strength, all that sort of stuff. So actual leak detection is happening autonomously at the hydrant level. Once you bring it up to the server, now we're looking at multi-channel. This is where you take all the nodes that have said, I hear a leak, you can put them in a group, and you can start to do correlation pairs. Now, by doing this, there's a whole bunch of other stuff we're doing at the back end, but this is how you now have a distribution leak detection system that has a very low false positive rate and a very high leak detection probability. We're running at around 87% for leak detection probability and a 3% false positive rate. This is a step change above published documentation from utilities that have tried out previous generations of this type of a system. So we'll go back and revisit the operational risks now with all that in mind. The leakage rate. This, we talked about how there's many more leaks and bursts that occur in a distribution system. There's more connection points and more chances for leak. So your leakage rate. In the past, you're queuing your repairs and you're fighting against the natural rate of rise of your leakage. Now you can queue repairs based on the likelihood of a burst. You can start to pick off the big leaks first, the most urgent leaks first. Customer service. This is the other big piece we're talking about here. You are repurposing your emergency response crews. They don't have to be as active. You're not talking about middle of the night holiday stuff necessarily. There's still going to be a need for them because there will still be some emergency work. But this system can reduce the amount of emergency work we're talking about. Labor costs increase. As labor costs increase, it just operational costs of utility get more expensive. That's going to force utilities to look at different ways to make labor more efficient. And public confidence. In the past, really understanding patients has been a big part of it. And it's been in the background and never necessarily talked about, but we've had a lot of discussions with a number of customers, and being citizens ourselves, we recognize this. Changing that to a proactive customer engagement, this could be very large for the public confidence. So monitoring leaks in the repair crew and mitigating all kinds of damage, and really just redefining it as customer centric. Mark?
And some of the things Eric is talking about, I'm sure there's people sitting out there and they're going, well, that's all great, but a system would have to be pretty reliable, sophisticated, accurate, sensitive, all these things in order to make this a reality. Because when I started in this field, really the holy grail was finding leaks very, very early and then intervening in them before they became catastrophic. And I still feel that is one of the holy grails. And being able to find not just 10 gallon per minute or 5 gallon per minute, but leaks that started a fraction of a gallon per minute. And Eric referred to some of the technology, and I'll expand on that. It's not just the sensor, but the algorithms we're using in our single node are very, very sophisticated. But that ability to send data to the web and correlate it is really what puts it over the edge. So, but that's all great, but does it really work? So
that's what we need to see, because we've been making a lot of claims here.
That's right. That's right. So does it really work? And the best way to show people that it works, and for those that have been on our other webinars, you'll recognize this slide because we keep showing it around. We have other cases of this, but this is from a pilot that we're doing with one of our development partners. And what you're seeing here is a correlation. For those who are not familiar with correlation, what you're seeing is the peak around the 2/3 mark on the right is a leak. And you can see that it's got a relatively low signal-to-noise ratio, as evidenced by how far the peak is from the surrounding noise. But you're seeing a graphical representation of two of those hydrant nodes that Eric showed you, and that's a leak. And the day before this did not exist. So we have seen this leak on the very first day that it started making any noise whatsoever. what happened with that leak then is we called our customer and we said, you have a leak there. And they went out and they put a commercially available correlator on it, and it wouldn't correlate. So the leak with the low signal to noise ratio, if those who are familiar with leak detection are out there, that would not correlate with the piece of equipment they put on it was not a bad correlator. It was a very good correlator. And we're like, that's fine, we'll keep watching it. So 2 weeks later, you can see this leak is getting stronger. And unfortunately, our client still couldn't find it. 4 weeks later, we're now thinking this leak is not stable. It's growing. It's getting stronger. Leak strength is not always a correlation of leak size. There's a lot more to it than that. But in this particular case, when you have a single leak and you're following it, it certainly is an indication of severity of the leak. So this leak has been running for 4 weeks now, and it's getting worse. So the client said, we can't find it. You guys come down and find it. So we sent one of our technicians down who has 30 years of leak detection experience with Severn Trent Water in the UK, where they're very serious about their leak detection. And we sent him down there. And even then, he said,
Is this where you do your British accent now?
Yeah, it was a bit dodgy. So when they excavated this leak, they started backhoeing down, and they ran into iron ore slag that had been backfilled on top of the pipe. And that was the reason our technician couldn't ground sound, is you had a giant noise barrier between us and the pipe. The other thing they found is they didn't actually see the water until they went 1 scoop below the pipe. That's a lesson for any of you operating water utilities. Don't stop at the top of the pipe. The leak was pointing straight down. And on the left-hand side, you can see the leak. It's pointing straight down. On the right-hand side is the piece of pipe we took out. And what you can see is a crack growing through the bell. And if you look very, very carefully, what you can see at the base of the bell is quite a bit of rust. So this joint of this bell had been probably seeping for a while. There was probably destabilized the soil, put a moment force on the bell, cracked it, and the crack then began to grow. And basically what our client thought was this is a time bomb delayed. We have no idea how big the leak was when we first saw it, but when we excavated it was around 5 gallons per minute, or about 20 liters per minute. But this ability to be able to find a leak and track it, and I should note that we've had other leaks for other clients in our pilots, where we had one where we tracked it for 6 months. The leak was stable. The customer finally got around to fixing it, and they thought that was the best thing ever because they just didn't have time to do it. It wasn't a serious leak, and they could deal with it and put it into a priority list. But again, this goes to show that this technology is not an old existing logger that somebody is repackaging into a permanent correlation system. This has been custom designed to be a permanent monitoring solution, and we don't see this as leak detection. We really see it as reliability-centered maintenance. Everybody does reliability-centered maintenance on the other components behind the fence of their water treatment plant. We feel this level of risk mitigation is now available outside the fence.
Perfect. Okay. So now where we've kind of started to skirt around the question of who can afford such a thing. I'm sure this seems like it's an expensive solution. Surprisingly, it's not, right? So let's talk about delivery models now. So one of the things we promise is this is tailor-made for small, medium, and large utilities. And these utilities have very different profiles. Your small and the small end of the medium may not have leak detection crews, may not have the in-house expertise to go ground sound, to do correlation, to do that sort of stuff. Often it's outsourced. Local firms will do this. A lot of leak detection crews out there will do that. At the large end, you've got leak detection crews. You might have 2 or 3 crews with correlators that are tasked with going out and surveying. Towards the beginning of this presentation, I borrowed from the Philadelphia Water. They're quite progressive. They monitor all of their mains. They go and survey all their mains. I think they're on a 3-year cycle, and I apologize for anyone in Philadelphia on the line if I've got that wrong, but it was very quick. It was around 3 years. So at the large end, and also we're talking different capital budgets here. So small and medium, managed service. This can be delivered as a managed service. We go in, we install the equipment, and we can remotely operate it. We can remotely do leak detection analysis. Because what we're really talking about here is we're just pulling acoustic data from the pipelines, we're uploading it to our servers, and we can analyze it. And location at that point where your specialists are becomes really irrelevant. And the communication is then through the user interface. Capital investment. This is where the utility will actually purchase the equipment. We do training, show them how to work the system, how to do peak selection and correlation, and really all the functionality of the system, and they can do that themselves. We are still available in the background for specific leak detection analysis. So we have points of interest that pop up that might be a little bit suspect. If it's not a clear leak, if you're not sure what's going on, our leak detection specialists are available in the office, in our control center, to do remote diagnosis. Really looking at these two simple models that have been applied to a variety of types of things, not just in the water industry, but any kind of computing or internet-based services. This will deliver permanently installed and effective leak detection to any of these systems. What's important to note too is it can be done in a phased approach. So you don't have to go out and blanket your whole city. Like let's say if you have a high non-revenue water rate, 30–35%. You may not want to go out and bracket the whole system in 1 year or 2 years. You can pick your areas where you're getting the most calls and the most leakage. Spend $100,000, $200,000 in 1 year, and then repeat that over 5 years until you've got your system covered off. And the thing to keep in mind, and it's the example we showed before, one catastrophic burst can pay for the monitoring system. There's a lot of things it's dependent on. You have to have it installed in the right place, and you have to catch that burst, and it has to be in a critical area. But this is a reality. So now we're coming to the end of the formal presentation. We'll open it up for questions shortly, but I want to start with another, or I want to finish off with another thought exercise here. So just a general questions to think about. As a utility, and we've got some utilities on the line, and I'm sure we've got consultants and other people as well. But if you'd imagine yourself to be a utility, do you do online monitoring for water quality, for things such as turbidity or for chlorine or things like that? Do your pumps have VFDs, variable speed drives? Do your high lift pumps have vibration sensors in the bearings? Is your production for both water and wastewater, is it controlled and monitored with SCADA? Well, these were all disruptive technologies that really disrupted the standard operation of a utility. And this is in a positive way. So now, if you imagine your future self looking back to your current self today, we believe that it will be inconceivable that pipelines were managed without permanent monitoring. One of the things we haven't focused on here or addressed is the economics of it. That will be the topic of an upcoming publication. We're going to look at the economic justification for that change. And with that, we're more than happy to answer questions.
All right, Eric, Mark, thank you guys very much. We're getting several questions coming in here from our attendees. Maybe we can start off with this one. Someone here asked, I've installed a similar system in the past on my distribution network and wasn't happy with the results. What is the typical performance of this system?
Sure, I'll take that one. The previous systems, and I'm not going to go into them specifically by name, but they kind of split off into two general types. And one was a system, as I said earlier, that was really meant to be a lift and shift. So you put loggers down, noise loggers down, you see where there's some noise in the system, and you go check out that area. And then there's other systems, early systems, that were essentially taking that type of technology and trying to install it permanently. But when we stood back and we looked at this, there were 3 or 4 areas that we felt these systems were lacking in. Eric alluded to the acoustic sensor. These are low-cost systems, and these very low-cost sensors that don't, and we've managed to overcome that with a low-cost sensor that frankly outperforms the sensors we were using on our correlator. We think this is a step change in sensor technology. The actual algorithms to determine whether there's a noise at a point and then the ability to send that data to the cloud and compare not just that, but with all the other points in the cloud, and finally to start correlating. And we correlate on very low bandwidth, so it doesn't affect our battery life. So these are things that, again, if you look at the technology and the ability of a company like Mueller that has incorporated a very good radio company with Mueller Systems with a very good leak detection company in Echologics, it's all one source, and it's not something I could have done without having that kind of corporate support and the team that we've got here as well. So we think this is an evolution that frankly has not been seen yet.
Okay, and then just sort of getting into failing pipes. I mean, obviously, pipes can fail just due to a variety of reasons, but how common is it that pipes actually leak before they fail?
It's a very interesting question. We hear this question frequently, and it's really a shame that there's not a lot of data on this, and it's just because you don't know a pipe has failed until it's failed. You don't know it's going to fail until it's actually already failed. But there are certain things we do know. There are types of pipes that do leak before failure. You've got riveted steel pipes. We know they tend to pop before and then unzip before failing. PCCP, there's leading indicators as well before a catastrophic failure. So what we can say with certainty is that we do know that leaks can lead to bursts. That's not to say that every burst doesn't leak first. So that's an important point to make, but looking at types of pipes that are out there and targeting types of pipes, there will be pipes that leak before bursting, and that's what the system is targeting.
And we look at it as the large and small pipes again. In our experience, and this is obviously not definitive, but the pipe failures we've looked at with our clients on large diameter transmission mains, I'm not going to say 100% of the time, but a very large percent of the time have evidence of a pre-existing leak. These pipes are massive. If you take a 24-inch cast iron pipe, it could be 1.5 to 2 inches thick, whereas the smaller pipes will absolutely fail spontaneously. But again, we've seen evidence in a great many failures that there's pre-existing leakage.
Yeah.
All right. And I'm getting a couple questions coming in here about the size of mains that the system is applicable to. One person asked, how reliable is this system with smaller mains? And then another person asked here, what's the largest size pipe you can work on? Maybe you guys could just reiterate a little bit about the size of mains that the leak detection system is compatible with.
Sure, you want to go?
So there really is no upper and lower limit. What I will tell you is the upper limit of the pipes that we found leaks on is 108 inches, or about 4 meters in diameter. The efficiency of the leak detection is going to be dependent on the spacing of our sensors. We specify everything based on our half mile or 750 meters on the pressure of the pipe. In general, leak detection on the smaller pipes is easier. So we believe we have very, very efficient, we can find the very smallest leaks on some of these small diameter pipes. On the large diameter pipes, again, in our testing, we found leaks down below 1 GPM on 36, 48-inch mains. It doesn't mean we'll always find that level of leak, but that's the type of performance that we can find. Our specification is
yeah. So for transmission, we're saying 16 inches and up. That's what we've tuned the system for, and then for the distribution is the 14 or 12 and lower.
And it should be noted that the sensor we use on the transmission mains is different. It's a hydrophone as opposed to a surface-mounted accelerometer on the smaller pipe.
Right.
Hope that answers it.
Yeah, I think so.
Yeah.
All right, and then a question on transients. What frequency do you use to monitor transients, and can you monitor as frequently as, say, 100 times per second?
So that's an interesting question as well. So I'm going to answer this from the transmission main point of view. So we're using a hydrophone, and the system is always on and it's always listening. and we do detect transients. We can detect transients, and we can also alarm those and send them out. In terms of data frequency,
yeah, we can tune that up to 2,000 hertz. Really, there's some debate on how fast you have to go. It was generally accepted that 100 hertz is acceptable. We're going to do some experimentation on comparing simultaneously 100, 200, up to 500 hertz, but it's programmable, and we can do just about any frequency that the client thinks is required.
Yeah.
So
and this is the functionality exists within the transmission main monitoring system. We focused on leak detection first because that's where we saw a big market gap, and that's where we were expecting to start to deliver these things first. But we also designed the system with that ability to expand.
Yeah, so we've got a lot of algorithms that we're working on. We also are going to be looking for acoustic transients that may indicate a burst, a sudden burst. We've already got an algorithm running on that. These are all firmware upgrades that we'll be able to do remotely as the system rolls out over the next year.
All right, and then on the system, you guys mentioned the low power mode. In low power mode, is the leak monitor listening, or does it just come on every so often or for a set period to listen and compare back the background noise signature?
So we have the always-on capability, but what the real power of the system is coming on once a day to do a very detailed leak noise correlation for the large pipes. What happens with the small diameter system is it wakes up in the middle of the night and takes a number of samples and analyzes those. If it thinks it's heard something and it compares that to its historical data, it will send that to the server, and the server may ask for a correlation as well. It's a bit of a convoluted answer, but the bottom line is that yes, the system is always on, it's always listening, but we think the real power of it is this ability to do these detailed acoustic samples, analyze them, and then determine the presence of a leak.
Exactly, and that's how we do the leaks on that 24-hour cycle. In terms of always on and listening, this is where we catch events. So like the transients, like a burst, and then the system has the ability to, there is a two-way communication here. We can talk to it, and it can talk to us, and that's an indication, or that's an instance where it talks to us.
Yeah, but again, one of the things that we feel is that by the time there's been a serious burst that would create an acoustic event, it may be too late. Not that there's not value in alerting to the utility before the news networks do, but again, the real power of the system is the 24-hour cycle leak detection.
All right, guys, and what about maintenance requirements? Can you provide any sort of insight into a benefit cost analysis for recent installation?
Yeah, sure. So
what are the maintenance requirements?
Sure. For transmission, the only consumable part is the battery, and the battery life is 1 to 5 years. If you're doing daily leak detection, you've got about a 1-year battery life. And these batteries they're field replaceable, hot swappable, and it's actually a very easy change. We've done this before both in practice and also in testing. It only takes about an hour and a half to replace a battery. That's including traffic control and everything. So that's going to be done. If you do leak detection once a day, you've got a 1-year battery life, and then it extends from there if you're doing less frequent leak detection. On the distribution side, we've designed it for a 5-year battery life, and as well these are field replaceable. So it's a consumable piece that gets replaced. It's not a throwaway device. The only other thing I guess on the transmission is there might be periodic maintenance on the hydrophone. There could be some buildup perhaps or something, but we would know that from the quality of the sound that comes in.
Yeah, and in our testing, we've designed that hydrophone specifically to avoid typical buildup. Yeah, we have a mineral phobic coating on it. We've done a lot of work on that.
So too much detail.
Yeah, but the system has been designed really to operate for many, many years with minimal maintenance.
Okay, and then have you guys done any studies on how much energy is saved from installing these permanent monitoring systems?
Interesting. The short answer to that is no.
But
okay.
That comes to the value of water, and that is going to come out in our next our next either paper or webinar.
Yeah.
And to give you an idea of a business case we did for one of our clients that was looking at a fairly large deployment of distribution leak detection, the savings per year were conservatively estimated at $5 million per year in water loss. The vast majority of that cost of water, some of it's chemicals and treatment, but the vast majority is electrical pumping costs.
Pumping the water into the ground.
That's right. And that was a client that had about 15% water loss. So that should give you some idea of the potential. We actually, if anybody's interested, they can contact us because we have a greenhouse gas spreadsheet that based on each state has a greenhouse gas footprint of their electrical system, and so we can calculate how much 1,000 gallons of water equate to in greenhouse gases, so we can go backwards and do that. But that's a good question.
A much more complete answer than I started off with.
And maybe just as sort of a part two to that question, though, are there any studies available, or are there any planned to I guess, address whether or not these monitoring systems can actually catch leaks sooner or reduce the number of leaks overall?
Yeah, I mean, I would say that right now our evidence from the pilot studies we've done is the one that we showed is not the only leak that we found early. And when we install these systems, as Eric said, we do a very detailed leak detection as well. So typically when we put these systems in, the existing leaks pop right up. And that's another advantage, is if you're looking at systems that are looking for changes in noise, they won't always find that. So the fact that we can correlate, identify, track them for several days, the answer would be yes. That's part of our business case. It's environmental, but it's also business. Water, electricity, energy, greenhouse gases are all intertwined.
It's a matter of time as well at this point.
Yeah, and sample size.
There's a large-scale installation that is just completed, and we know what the non-revenue water was at that site, and now it'll be an interesting year for us. We're going to find out what that drops to, and we're going to find out how many leaks are found. We're going to find out what the volume of those leaks were. We're going to get all kinds of good information.
Natural rate rise.
Well, we're hoping to see the natural rate rise at the very end of the year, but I'm getting ahead of myself, so stay tuned, I guess, is what we're saying.
Okay, and then a quick question here on managed service. Who actually owns these sensors?
So on the managed service piece, then the way it would work is we've got a few models that we follow, but in general there's essentially what is a lease to own type thing, where we would essentially be the capital provider. And then the equipment cost is paid back over time at an interest rate. Then ownership would transfer over a period to the utility. The thinking there is that it would, by that time, they would most likely be able to have the expertise in-house to do it themselves. If that's not palatable, then we retain ownership, and then the benefits to the customer there are they get all the upgrades, both hardware and firmware are included as part of an annual subscription amount.
Okay, and then a question came in here about temperature and I guess the effect that has on the systems. Does the system perform in, say, tropical areas with temperatures up to 40 degrees Celsius?
Yeah, so environmental temperatures we're good over 40 degrees C. In terms of water temperature, I forget what it is. It's over 30 degrees C for water temperature. Yeah. So the answer to that is yes, it performs in tropical climates. We've designed this like knowing that chambers in the road, for example, for the transmission system, they can get hot. We had an installation in Texas where it got hot, right? You had a dark manhole cover that heats up, and the same thing with hydrants. Light colors are going to reflect the light, but you're getting a solar load on there in addition to just a temperature. So yes, it is good for a tropical climate. And
that goes not just for the electronics, but the batteries. We use very high-quality batteries as well. We know that battery can be not only affected by low temperature, but very high temperature as well. Again, being part of Mueller, we have access to environmental chambers. If you look at the quality control done on our equipment, it's all manufactured by Mueller Systems, in Cleveland, North Carolina. The boards are 3D X-ray to look for faults in solder or cold solders. There's a very, very high level of engineering and quality assurance that goes into this. It's probably unprecedented in most of the fields of leak detection.
Okay, and then just getting into background noise a little bit more, are there any high noise environment areas, like urban areas, where this leak detection technology has trouble functioning?
So there's a couple ways you can answer that. So the first part of that, the answer is yes, absolutely. There are high noise environments. I don't know, let's just off the top of our head, maybe like a Las Vegas Strip or something like that, where there's lots of people and noise and slot machines and stuff like that. We have experience on the mains that run under the Las Vegas Strip. And then Mark, you want to answer the second part about?
Yeah. So we've one of the downsides of putting a system above ground is that it is exposed to things like wind, to rain, to external noise. The electronics that have gone into this are very sophisticated. It's not just a standard piece of electronics. Suffice it to say that these are all things that we had to overcome, and our pilot testing has absolutely undergone in very noisy environments. So yes, without going into too much detail, technical detail that I don't have time to go into, this has absolutely been part of the development process, is to consider that.
All right, and guys, I think we have time for one more question here, and then we'll start wrapping up. And as I'm looking at some of these, perhaps this is a good one to end on. Someone here asked, any thoughts of permanent sewer leakage detection?
So that's a great question. Some of that, I mean, depends on what you're talking about. There's a lot of different types of sewer detection, but what I will tell you is that our equipment works on pressurized mains. So we could certainly adapt this for pressurized sewer mains, but no, we're not currently in the field of gravity sewers.
Yeah, so like for infiltration type things, or like ovality of the pipes, that sort of stuff is not currently, our technology doesn't focus on that.
That's correct.
So the short answer is yes if it's a force main, and unfortunately not if it's a gravity sewer.
All right. All right, very good, guys. Well, we can go ahead and start wrapping up. And Mark, Eric, thank you guys very much. It was a great presentation. And I'd like to thank you guys, and like to thank all of our attendees for joining us this afternoon, and also to Ecologics for sponsoring today's webinar. And just a message to all attendees that we're going to be providing everyone with a public version of the webinar, so they'll be able to sort of review everything that was discussed today. And also any questions that came in from attendees that the presenters didn't get to address. I know the folks from Ecologics will certainly follow up with the attendees and make those responses available. And if there's anything that any attendees missed or would like to go back and refer to, this webinar will be archived at our website at www.uimonline.com. So thanks again, everyone, and we look forward to having you join us for a future webinar.
Thank you.
Thanks, guys.